Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are 5 modules. Now we'll be going adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Thank you.
Good morning to all of you. Welcome to class 6 of my first year physics courses, PH 1 through 1. And by this time I illustrated many things. We are in the studies of quantum mechanics. Okay, and quantum mechanics 1, and quantum mechanics 1 means we have to learn a lot of experiments, a lot of theory. Okay, and each day, each experiment is giving us some new lesson. Okay, so let us get into the business. Okay, you can see it's a long way to go. 36 lectures. We are only in the 6 lectures. Okay, so this is the course topic, quantum mechanics 1. This is me, and just again for information, any problem, okay, you can contact me in my email IDs or the phone numbers given, or there is also my WhatsApp number. Okay, now I started everything just to remind you what we have been doing. We start. This person is the father of quantum mechanics, Max Planck. He did an experiment with black body. Every day I'll remind about Max Planck to you, because he is the father of whatever you have been doing, father of quantum ideas. So what Planck did, Planck actually explained black body radiation. Okay, and the what is the black body, that I told you, and what happened in the experiment of black body radiation, that you can see on the screen. A black body was heated from a temperature T1 to a temperature T2. Because of that, it had emitted radiation, and the corresponding energy for each and every wavelength was measured and plotted, and you get a graph like this. Okay, this graph was obtained, that you can see on the screen. This graph was obtained. This is the experimental graph of black body radiation. It's a peculiar graph. Initially, it goes up, finally, it goes down, and in between, it passes through maxima. So we wanted to calculate what is the total energy emitted by the black body. So in order to do that, we have to do that integration. But you can only integrate it if you know the formula of E lambda. Now the question is that, do you know that? Answer was very bad initially. We did not have the right expression of E lambda, because it was not falling into our known curve. Okay, so because it is not falling into this our known curve, so what would happen? So we tried to explore about various propositions about E lambda. The first proposal came from Wien. As you know, it was an incorrect proposal. So later on, Rayleigh came into business, but the correct proposal was given by Max Planck. And Planck's third assumption, okay, when he was explaining black body radiation, that you see, this is very important, this line. The energy of an object is discrete. This is the Planck's idea. Energy of an object is discrete. Okay, there is the first person in the art to think that any energy of an object, okay, is multiple of quantum of energy called h nu. Okay, so that is a major contribution of Planck in the development of the history of physics. Okay, so that is something, that is the only thing we should actually take away when you consider the larger perspective of quantum mechanics. So Planck has presumed, okay, Planck has proved his idea, because we have applied this idea to explain that experimental curve of black body radiation. Okay, this discretization of energy. Main difference is that if you follow the classical theory, okay, energy of the objects are, all energies are possible. Okay, all energies are possible. If you look at this yellow line, okay, all energies are allowed. There is nothing disallowed. Okay, but according to Planck, what is happening? Only some discrete values are allowed. Only some discrete energy levels are allowed. Okay, so this discretization of energy, quantization of energy, everybody talk later on, but Planck is the first person in the art to think about it. Okay, even the shampoo company is also doing it now. You see, when 10 years back, if you have to purchase shampoo, we get a say 5 liter, 1 liter bottle. Now, if you're staying in the hostel, do you get take 1 liter bottle? You have got series of sachets of shampoo, each of 5 ml. Okay, even we also purchase shampoo in as a sachet. Okay, what we are doing? Shampoo company has quantized the shampoo. What is the one quantum of shampoo? 5 ml. So if you need 100 ml shampoo, what you do? You get 20 quantum of shampoo. Okay, or 20 quanta of shampoo in plural. So basically, this quantization means you are getting something which was thought to be continuous into pieces. So Planck did it. Now everybody is doing it. Okay, Planck is the first person to do it. Now later on, Bohr followed him. I mentioned last day. The our Einstein followed him. Got the Nobel Prize in winning photoelectric effect was explained. That was the same idea. Energy is discrete. So basically, whatever Planck has assumed, whatever Planck has proposed, okay, we'll try to now establish that through some breakthrough experiments. So now, what should I do? Actually, I divide physics into two parts because 1900 is the year when Max Planck has given that wonderful idea that energy of an object is discrete. Okay, so Planck is giving you that wonderful idea. So we'll consider that 1900 as a benchmark year, as I have marked with orange lines there. Now, before 1900, it is called classical physics. You see, I put a barrier there. Why? You should know it. And after 1900, it's called modern physics. Okay. Now, classical physics means the physics you know from your school days. Okay, the physics you studied in your earlier life. Actually, the physics you know is classical, and you see it has got a barrier in its own concept. How? So that let me tell you now. Let me just illustrate what is the physics you know. What is the classical physics mean? Now, the physics you know is this much. You see, is you started learning physics in your early life in schools with units and dimension. Then you have been given the basic idea. Any physics course anywhere in India, in US, in Japan, Nepal, China, Pakistan, whatever it may be, anywhere, any physics course starts with units and dimension. And it is followed by the basic concept of motion. What is static condition? What is displacement? What is velocity? What is acceleration? And then Newton comes to your class, and Newton teaches you a few lessons. What Newton tells you, he defines what is called force, Parts law. Okay. Second law, Newton gives the formula of calculating force, force equal to mass into acceleration. Second law. And third law, what is the impact of force, the concept of reaction. And if you look at your earlier life, you saw hundreds of problems with this idea. We applied that in the normal rectilinear motion. We applied of the problem if two bodies collide. Okay, we applied that problem if somebody rotates. We applied that problem if somebody is under friction. We applied that problem if somebody is falling down along a slope. You applied that in the problem in the explanation of gravitation idea, in the concept of Newtonian, that is also Newtonian idea, the gravitational formula. So everywhere, even in the general properties of matter, the concept of elasticity, okay, the concept of restoring force is coming. So that is also Newtonian idea, because Newton has told to think in this line. First, you know the root cause of whether a body will move or not. That is a force. And what is the estimation of force? That formula is given by Newton. So even elasticity, when you define force equal to minus kx, you are following Newton, and after that you solve it. And it may be the oscillation problem, harmonic oscillation, damped harmonic, force vibration. You learn in this semester also a bit. Because they've got electrical equivalence. So there also the variety of forces comes into business. Normal force, the harmonic force, the damping force, the force vibrational, external harmonic forces. All these things are coming into business. Okay, all everywhere you are following Newton, nothing else. Even the surface tension and viscosity. Surface tension means force along the tangential force on the surface of a fluid that makes the a fluid like a sphere. And and you also know the viscosity. If fluid flows, there will be resistive forces against the flow. So basically, there are variety of ways you applied this idea, and everywhere it is all Newton, 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 Newton. So majority of your studies, you may be solving hundreds of problems in your while preparing for joint entrance examination or any competitive examination. But these are all the problems of motion. Either a matter moving, either somebody fluid moving, fluid flowing, either somebody a spring is vibrating, either somebody rotating. All are mechanics problem, motion problem, and everywhere you have taken the help of Newton. You apart from these, you studied a bit of reflection, refraction. There's a study of light waves, the study of sound waves. Okay, sound wave is also mechanical vibration, you know. Mm. And you studied a bit of the laws of reflection, refractions, dispersion, how what happens light through passes through prism. And there you don't use Newtonian idea. There you have got separate law. So it's another world that we explore, the world of waves, and namely electromagnetic waves, the light waves are called. Sound waves also you learn, the Doppler effect, etc., etc. But there also motion concept is inbuilt. So pure electromagnetic theory, or the pure, when you explain electromagnetic waves or light waves and their optical phenomena, you use a completely new physics. Okay, it may be reflection, it may be refraction, it may be dispersion, or even you might be knowing interference diffraction. Okay, so there also it's altogether there Newton is helpless. So and later on you learned a bit of electricity, electrostatics, the forces between charges. Okay, now you look forces between magnetic poles, that is also Coulomb's law. You see everywhere, whatever with the theory you are using, they're very old theories, because Newtonian idea was proposed nearly 400 years back. So it's a classic, that's why it is a classical concept. So majority of the mechanics problem, somebody may be in a linear motion, rotational path, frictional motion, fluid flowing, somebody is under elasticity, any type of problem, as a matter of fact, to solve are application of a 400-year-old concept. Even the laws of optics also, the Snell's law, the Rayleigh criteria are proposed much before the year 1900. Okay. So any physical concept coming before 1900, henceforth we will be calling classical physics. And you see, you know it. Later on, you know, and learned about current electricity, Ohm's law, Joule's law, proposed much before 1900. Okay. So even in the basic electrical or electronics, we are applying the Kirchhoff's voltage law, current law, proposed much before 1900. Even the entire mechanical science we are learning also. The majority of the topics is a D.L.M.'s principle, proposed much before 1900. So the level of theory might have improved, but these are all major application of physics before 1900, and altogether we call them as classical physics. It may be mechanics, it may be wave theory, it may be electrostatics, that is forces between charges, magnetostatics, forces between magnetic poles, electromagnetism, that is the change in magnetic field producing electric field, that is Faraday's law. Okay, it may be the idea of the current electricity, Ohm's law, Joule's law. Majority of these topics are old physics, classical physics, proposed much before 19. And they're right. They're still till date they are valid. Okay, and you know them. Majority of them you know it. And only thing is that so most of the things, just the basic similarity is that all of them are proposed before 1900. So all of them with henceforth will call them as classical physics. And this thing you know it. You just see now, and the physics after 1900, I am now benchmarking as modern physics. In your school syllabus, you learned a bit of some experiments, okay, which are done, uh, done after 1900. It's a photoelectric effect, which all of you studied, 1905. Radioactivity, 1913. Or 1909 or 10, I'm not exactly recollect the actually, yeah. The Bohr's theory, okay, 1913. Okay, you studied all these things. Entire electronics, okay, the concept of junction diodes, transistors, logic gates. They're much more relatively new topics and proposed long after 1900. So basically, these things, if you look back your school day book, they are under the heading of modern physics. So physics before 1900 henceforth will be called classical, and physics after 1900 henceforth will be defined as the modern physics. Now, classical physics you know, and modern physics a bit you know, and we have to explore more. And this modern physics is actually the mainly based on the quantum ideas, because in 1900 Planck has given the first quantum concept. Okay, he has given the first quantum concept in the year 1900. So now let me just remind you what you know classically. Classically, you know there are objects can be of two types. Some of them are explained through mechanics, methods, and some of the other one, some of them are waves. For example, this pen. This pen is a matter because it has got a definite size. Can you tell me which one is a pen and which one is a remote? Anybody can tell it. Okay, I hope you can see it. Okay, how do you know it is? Okay, who tells you it's a pen and who tells you it's a remote? Because you see, nothing is written here. REMOT is not written here on the screen. Pen is not written on the surface of the pen. Then how do you differentiate? Because you know from our old knowledge, a pen looks like this and a remote looks like this. Looks like this means I'm talking about its geometrical shape. It's like a cylinder and it's like a rectangular parallelepiped. So both of them are matter. So how do I know them? How do I differentiate them? Both of them has got definite geometry. Okay, geometry. Okay, so a matter should have definite size. Geometry means definite size, definite shape. This is like a cylinder, and this is like a rectangular parallelepiped. Okay, they both of them have definite mass. If they move, both of them should have definite momentum. So these are the attributes of matter. Okay, so matter a clock. Okay, the car is a classic. We are also matter. The car is a matter. Train is a matter. Bus is a matter. So in mental mechanics problem, we have been only talking about matters. It may be very large size like car, maybe small size like pen, or even much smaller. Our favorite electron is also matter. Okay, because it has got a definite mass. Okay, 9.10 to the power minus 31 kg and etc. And the other side of the story is waves. Suppose I'm talking, I'm generating sound wave, but do you see a football of sound is coming from my mouth? You can't see because it does not have a shape and size. So wave does not have a shape and size. Even if I talk also, and if you are sitting in front of me, it will be painful to your ears, but as such you do not feel any pain because the sound emitted does not have any mass. So it does not have this material attribute, no mass, no size, no shape, and obviously these things are the other part of the story. We call them as waves. Okay, okay. We call them as waves. Waves may be of two types, as everybody knows: sound wave or acoustic wave, created by mechanical vibration, or maybe the light waves. Okay, the electromagnetic wave. And how do I define waves? By their other terms, not by mass, momentum, etc., by wavelength, frequency, and phase. So two different worlds. For waves, some defined feature. For matters, different feature. I do not say a car has got a wavelength of this, or I do not say a light wave has got a mass of this. I do not say this. So this is your classical concept. Waves are different, matters are different. To explain waves, you use the wave theory, mainly based on reflection, refraction, dispersion, these things, interference, diffraction. These are the optical phenomena, all of them actually are called electromagnetic wave. Later on, you'll know electromagnetic theory of Maxwell in our course only. Okay, and for matters, actually, you have got your Newton to help you in majority of the problem. So two different world, two different types of physics you studied. Okay, now what I might take course will tell you, I'll talk about some experiments before 1900. This will just shatter your classical concept. It will show a huge departure from the classical idea. What is your classical idea? Matters are different, waves are different. They do not talk with each other. For matters, I've got Newton to help me with mechanics, and for waves, I've got wave theory to help me. So two different worlds, so two different class of physics. So what shall I do? I'll talk about some experiments which will break this idea, break these jinx, whatever you know from classical physics. And that is the beauty of modern physics. Okay, so let us get it. It's something wonderful is waiting. Okay, you see the car, you see what the car is doing. Oh God, it is colliding. Okay, but who collides? A matter collides. Okay, mind it. So just see, if 1900 is a benchmark here, you please see what classical physics is telling you, that a matter has got mass, momentum, size, and what is the best exhibition of material nature. Suppose two pens are there. What the pens are doing? Pens are actually colliding. If they comes in opposition, they will collide. That is what the car is doing. So best exhibition of the material nature is basically collision. Okay, matters do collide, and collision means keep fighting. Okay, who can fight? Who has got momentum? Who has got mass? So matters do have, the car do have it. It's mass and momentum. So it is colliding. Okay, it is colliding. the car is colliding. Okay, so it is showing the, so who can collide? A matter can collide. Okay. So best exhibition of the material nature is collision. Just a second. Because only matter can collide. On the contrary, what is a collision means friendship. Friends will fight. Sorry, collision means fighting. Collision means no friendship, fighting, collision. So who collides? Who has got some energy? Who has got some momentum? Who has got some mass? Okay, for momentum, collision is momentum is an important parameter for collision. I hope you know from your school day. For any collision, momentum is conserved. Okay, and collision will be elastic, inelastic, semi-elastic. Only for elastic collision, energy is also conserved. Conserved means total energy before the collision and after the collision is the same. On the contrary, waves, if you look at the waves, okay, you see what these waves are doing. Waves can, the best exhibition of the wave nature is superposition. Okay. So basically it is, so therefore you can see here that as I was mentioning, that the best exhibition of wave nature is therefore the superposition, because superposition means friendship. Two things should be there at the same position at the same time, which is not possible with matters. If I have got one matter in my hand, suppose this pen is in my hand, now between my fingers. Now, can I keep a second pen here? I cannot keep it. I can keep it after some time. Okay. Superposition means two things should be there at the same position at the same time. So that means I have to keep two pens at the same position. Is it possible? Is it possible? No. I can keep them at the same position. I can keep it after some time. That means I'm not violating at the same time condition. Okay. Okay. So now first condition is that I have to keep them at the same time at the same position. So I'm keeping them at the same position, not at the same time now. Okay. So if I try to, so these are the two matters. I cannot keep them at the same position at the same time. So if I try to keep them at the same position and same time, what is happening? They are colliding. So matters, if you try to superpose before superposition, they will collide. I sorry. Now if this pen is there and if I try to keep the second pen here, what it will try to do? It will collide. It will try to dislodge it. So what it is doing? Okay, matters because they have got momentum before collision, they will make before superposition, they will start colliding. So that's why we say henceforth, if I talk collision, I'm only talking about matters because matters can't superpose. And if I talk waves, so talk superposition, I'm only talking about waves because waves do not have any mass, momentum, etc. They can superpose only. Okay, so if I say superposition, I'm only talking about waves because matter cannot superpose. Opposite story is true. Waves do not have any mass and momentum; they can't collide. So collision is exclusively material property, and superposition is exclusively wave property. Only matters can collide. Only waves can superpose. Okay. Only waves can superpose. That is the concept. Okay. Okay. Now, henceforth, you should keep this mantra in mind. So if I've got two matters coming in opposition, they will collide. And if two waves comes in opposition, they will do superposition. Now, the idea is that another thing can also happen, that if a wave is incident on a matter, there is earlier wave superposing, matter colliding. Now, wave on a matter will do scattering. Okay, you can see there scattering is taking place. Sunlight is an incident on the dust and it is getting scattered. Another example of scattering I show you here, the classical examples of scattering. Normal reflection. Suppose I have got a surface, is a mirror, and some light is incident. What would happen if no mirror was there? It will move straight forward. And because of the presence of the matter, what it will do? It will be reflected. So what is reflection means? It is not following the initial path. Rather, because of the presence of the mirror, whatever be the wave coming in, it is getting deviated. Okay. So this, it is not following the initial path. So this departure is actually called scattering. So this angle is called the alpha, the angle of scattering. So what it is doing, it is getting scattered. Okay. So wave on a matter makes the scattering process. You see, I have underlined the word scattering process. Okay. Wave on a matter makes scattering. So wave superposes. Okay. Matter collides, and wave on a matter, wave incident on a matter means it will lead to collision. If no matter was there, it will move straight. You can see here. Okay, if no matter was there, it will follow this path, it will move straight. Now, if you keep a matter in front, suppose this is a mirror, if you are keeping a matter in front of it, okay, what it would do? Normal reflections are examples of this. That's why I'm taking reflection as an example. So if a radiation coming in, so what would happen? It is not following this path because it is restricted to move. So it will be deviated from here. These deviations, this departure, okay, is called the scattering. In normal reflection, what you knew is this is the angle of incidence, this is the angle of reflection. Okay, so basically it is deviated from the initial path. So I consider this as the alpha, the angle of scattering, because this was the initial path. Okay, the angle made with the initial path is the angle of scattering. So it is not following the initial path. Okay, this is the angle of scattering, angle made. Okay, so it is scattered. Any example, suppose any radiation coming in like this, an incident on any matter, so it was supposed to move along this direction, and suppose it is deviated like this. Okay, now this departure, this was the initial path, it was supposed to move in this direction. Now it is deviated by some angle, say alpha. So this alpha is basically the angle of scattering. So if the radiation of wavelength lambda coming in, it is getting scattered. Okay, and so basically normal reflections are the example of this. Okay, so this is the scattering angle, and the phenomena is the scattering phenomena. I hope you understand. Okay, so now therefore if you look at the entire phenomena, before 1900 it's all classical. The matters are there defined by their mass, momentum, size. Matters can collide, waves can superpose. Wave on a matter makes the scattering phenomena. Okay, now these ideas are going to shatter the moment you learn these two experiments on the screen. One of them is photoelectric effect, another is the Compton effect experiment. Okay, photoelectric effect and Compton effect study. Okay, now what happens in photoelectric effect? Okay, you please see, let me just explore both the experiments together. Photoelectricity, as you can see on the screen, on a metallic surface, it happens with metals only. Auditory light will be incident, that is called photosensitive surface. And what would happen because of that? After incidence, it will be scattered. Okay, you see, on a metallic surface, okay, light is incident, and what would happen because of that? This phenomena is expected, as I've shown in the right side here. You see, light is incident on a metallic surface. Okay, so it is incident on a metallic surface. Okay, incident on a metallic surface. Okay, so what is happening because of that? Electrons are coming out of the metallic surface. This emission, this phenomena is called photoelectric effect. So now if you look at the phenomena, it is the situation is that those yellow lines are like waves coming in, and they are incident on the matters. Okay, so these are the electrons. They are incident on the matter. Okay, so phenomena is like that. Okay, this is a metal, and this is one of the electron of the metal. On the metallic electron, what is happening? Radiation is coming in. Okay, radiation is coming in. So radiation is coming in of say wavelength lambda greater than some frequency. Sorry, uh, less than, actually, not greater than. The frequency is greater than some frequency called threshold frequency, and wavelength is greater than, less than some wavelength. We may call it lambda 0. In any case, that story you possibly be knowing from school day. So radiation of wavelength lambda is coming in. It is incident on one of the electrons. So it's a wave incident on a matter, and it is appearing to be a scattering phenomena because wave on a matter makes scattering. So we should anticipate that we should get a scattered beam. But in photoelectric effect, do you get a scattered beam? You do not get the scattered beam. Rather, what you get in photoelectricity, these electron actually comes out of the metal. This electron goes out. These electrons are emitted out of the metal. That is the beauty of photoelectric effect. Now you see, according to classical physics, it appears to be a wave incident on a matter because electron is a matter. Okay, it has got a definite mass, m0, 9.3 10 to the power minus 31 kg. So wave incident on a matter seems to be a scattering phenomena. But you see, instead of scattering, we are getting an electron emission. So what is happening? Your classical physics is failing again. You see, classical physics tells me it will be scattering phenomena. Then you should end up with a scattered wave. Okay, this should be the scattered wave. But I am not getting the scattered beam. Rather, I am getting the electron emission. So if you use classical physics, that wave on a matter makes scattering, so I should get a scattered beam. But my result is that I am not getting scattered beam, rather I am getting electron emission. So if we use classical physics, the big question is that where from this electron is coming. So with your classical physics, you cannot explain the electron emission. Just apply your common sense. We know three things can happen in nature. Waves will superpose, matters will collide, and wave on a matter scattering. It seems to be a scattering phenomena according to the classical idea, but I'm not getting a scattered beam as output. I'm getting electron emission, as you can see in the picture also, that okay, electrons are coming out. Okay, we are getting electron emission. Okay, we are getting electrons are coming out, and okay, and you get a, as measured in the experiment, you are getting the corresponding current also. So with classical physics, you cannot explain why the electron is coming out. And all of us know how Einstein explained it because you studied it. Okay, if the radiation is coming in, okay, that is the phenomena taking place. The electrons are coming out, whatever I have been telling you. Okay, it's a beautiful animation, na? Electrons are hitting. You see, there are two pictures are very significant. Okay, I have used orange, yellow color and green color. With yellow, I told you see, I have shown there is no electron emission. But with green, you see electrons are coming out. This teaches you another, reminds you that fact, the concept of threshold frequency, that for even for electron to emit also, you need minimum frequency, some minimum frequency, nu zero, that is called threshold frequency. And above that, it's very good. So you see with yellow, the frequency of yellow color is lesser than that of the green. Okay, that's why with yellow you are getting nothing. Okay, so that means yellow may be below the threshold frequency of that particular metal. That threshold frequency will vary from metal to metal. Okay, that is called the term called photoelectric work function is associated. You possibly be knowing from school days. So basically, with yellow I get no electron emission. So it is all happening beyond certain frequency. Okay, so frequency of green is above the particular threshold frequency of that particular metal I am showing on the screen. So with every radiation you cannot get electron emission. You need specific radiation of specific wavelength. So two things here to be noted, that if I use classical physics, it seems to be a scattering phenomena, but with scattering theory I cannot explain where from electrons are coming. So it's a failure of classical physics. Okay, and so you have to explain, and for many observations are there, all the phenomena, electrons are coming but not coming always. Okay, it is coming after above certain frequency or below certain wavelength. Okay, so that means many open questions are there. Why electrons are coming? Because electrons are not expected to be there, and they are coming. Why? That is only for above certain frequencies, at and above some certain frequency. So many open-ended questions are there, and which classical physics failed to explain. That's why Einstein has to come into business. So Einstein, what he did, he explained photoelectric effect. You see, as I have shown you, whatever I told you, it is similar to scattering phenomena, but you cannot explain it. Okay, this is something I was shouting about. Okay, it is with scattering theory you will be failing to explain. I hope you realize whatever I have been trying to tell you. Okay, so Einstein explained it. That is an experimental setup of photoelectric wave. You see that radiation is coming in, hitting the metal, electrons are coming out, and you get the current. Okay, very beautiful picture. So these are the results of photoelectric effect. Everything began at some frequency nu zero, but if you the kinetic energy term will grow up with frequency, but it's and with intensity, more and more electrons will come out. Okay, if intensity means more and more photons are incident. So these are the basic concepts. Okay, and above threshold frequency, you can see the right hand side picture. Okay, and current does not grow with frequency because it depends on the number of photons. Okay, so many number, oh, sorry, photon you do not know number, it depends on the intensity, on the amount of light falling. If more light means more electrons will come out, so I'll get more current. So frequency variation has got no impact on it. So these are the observations of the experiment that was done in photoelectric effect, which you might be knowing from school days. You can visit that virtual lab setup I presented there. The lab, this photoelectricity is a school day concept, so this experimental setup is not in our course, but I recommend you to go there. Okay, you have to do a small registration there. You visit it. It's a, this is, you get a real life experience of whatever you have been doing in studied in 10+2 courses. Okay, now Einstein have to come into business, and Einstein went to given two ideas. First idea, you know, he used photon concept. There is light means light is not coming from the incident radiation. Okay, is not providing energy continuously to the metallic surface, rather discretely. Each discrete packet of energy is called photon, whose energy is h nu. And when it is interacting with the electron of that particular metal, at a given time, an electron can interact with only one photon. Electron can absorb only one photon. So what happens here? Look at the experiment. Okay, you see this electron is coming, the photon is coming, it is being absorbed by one of the electron, and electron is going out. So two things are involved. Okay, photon is coming. Okay, it is absorbed by the electron. Okay, so at a time, first idea is that photon is coming. The yellow one is the photon. Photon is coming. At a given time, an electron can absorb only one photon. Okay, it can absorb only one photon, and with that photon, what electron is doing, it is overcoming the attraction of the Coulomb, Coulombic attraction of the nucleus, and ultimately going out of the system. Okay, so this is the picture. And the question is that the concept of threshold frequency automatically comes if the photonic energy is sufficient for the electron to overcome the Coulombic attraction, then it will be coming out. Otherwise, electron cannot come out. Okay, actually, this is happening. Okay, you see, this is happening. Photons are coming in. Later on in my Compton effect experiment, I will show you. I will calculate the photonic mass, photonic momentum. So we define photon as a matter there. Photon is a matter with some energy, some mass, some momentum. So what the matter photon is doing there, matter photon is hitting the electron. Okay, so now this phenomena is taking place. You see, look at the picture here. Initial energy of the photon is h nu. Now what photon is doing, okay, this is being absorbed by one electron, and electron is absorbing that photon. So this electron, you see, this is under Coulombic attraction of the nucleus. Okay, it is under the Coulombic attraction. Okay, this electron is under Coulomb attraction of the nucleus. Okay, so what you have to do is you have to do this absorption of the photon. It has to overcome the Coulombic attraction. Okay, and the amount of, so whatever be the energy absorbed, energy taken by the electron, a portion of the energy will be lost in overcoming the Coulombic attraction, which is called W0, the photoelectric work function. If you choose, it depends on the electron Coulomb nuclear interaction. Okay, it's the Coulombic interaction, the electron nucleus interaction. If the atomic number is Zd, okay, say plus Zd, the nuclear charge, and electron charge is minus E, and it would be like 4 pi epsilon naught and atomic radius square. So basically it depends on Z, because for a given atom to atom, R is almost 10 to the power minus 13 meter or so. So from atom to atom, for heavy atom, Z will be more, Coulombic attraction will be more. It is difficult for the electron to overcome Coulomb. More, you need more energy for electron to overcome the Coulombic attraction. For lighter atom, Z is less, Coulombic attraction is less. So you need lesser energy. So basically this will vary from material to material, and ultimately electron has absorbed h amount of energy from the photon, losing a bit of energy W0. So with the remaining energy, it will come out of the metal, okay, as I've shown in the previous picture, and this will appear as the kinetic energy of the electron. So this equation, as you know, is a famous photoelectric equation of Einstein. Okay, my job is not to teach you it again. You studied in school days. I only explained it. My job is to tell you is that you are using, how you are getting this. You are getting this with this concept, that with this beautiful picture actually, that photons are coming in, it is being absorbed. Okay, and what photons are, photon is like a matter, it has got definite mass. We'll calculate the definite mass. Photon is a very low mass, h2 by c square is a very insignificant. It has got a definite momentum, which we'll calculate later on, h2 by c, the almost insignificant mass, h2 by c square. So it moves, it has somebody with mass and momentum, according to our description, is like a material, is it has got material feature. So photon is the material, has got material property, it has got definite energy, definite momentum, somebody with mass, somebody with momentum, is that means it is showing the material property. Now matter photon is hitting the electron, so it's a photon electron collision process. Okay, so that means we are explaining everything not with a scattering process. A matter photon is hitting electron, so basically it's a collision mechanism. Who collides? Matter collides. So you are thinking, you are explaining whole phenomena with a material concept, because you know, as I told you, only matters can collide. Okay, waves can superpose. Wave on a matter makes scattering. Initially we thought it's a scattering process, but with scattering process I cannot explain electron emission. How do I explain? We explain the whole process as photon electron collision. Who collides? Matter collides. So to me, electron is a matter, we know, everybody of us know it, but to me photon is also showing the property of matter. Okay, photonic mass, we'll calculate, I'll show you the calculation. Photon has got a definite momentum also, h nu by c kind of thing. So ultimately the main message is that it is an experiment where you are considering light, okay, not showing the electromagnetic radiation. Light will be showing, not showing the wave property scattering, rather it is showing the, rather it is showing the particle property. Okay, rather it is showing the particle property. Okay, the material property, photonic property, okay, material property, because it is colliding. Okay, so basically some pertinent examples are there. Okay, so the takeaway from this class is this photon concept. Takeaway from the class is a departure from classical physics. What do you learn from this class? Outcome of the class, that it's a departure from classical physics. Classical physics only defines the electromagnetic wave, light as a wave, but this class is telling us no. In the photo, at least one experiment is there where I cannot explain the electron emission from the metal, electron emission from the metal with wave concept. Okay, I have to explain it with the particle concept. Okay, because only it's the whole phenomena is explained as electron photon collision. Who collides? Matter collides. Okay, so photons are showing the material feature. Okay, so that is only thing. It's that this is something, because all of you studied photoelectricity in school days. So my point is that to pinpoint that what it teaches you a departure from classical physics, that it's an experiment showing the deviation from classical physics. Light is regarded as a stream of photons. Photons are showing the property of matter. What is the best exhibition of material property? Collision. Okay, so that is something is done. Now this is an example where you can see you have to calculate the photonic energy. It's very simple. Okay, energy is wavelength is 486 nanometer. C is there, H is there. You put the values. Okay, mind it. This will be in joules. Okay, you have to get it in electron volt. But if you divide this quantity by this much, okay, 1.602, because at the atomic level, energy is calculated in electron volt. 1.602 into 10 to the power minus 19, that is joule to electron volt conversion. Then this will be converted into electron volt. Okay, then this will not be in joules then. Okay, so that you can do. Okay, 10 to the power minus 19, 10 to the minus 19 cancels out. 1.6 is close to 3 by 2. So basically it goes 8 by 3. So it is 3 point, close to 2 point something electron volt. Okay. Okay, so this, what is the outcome of this entire study? As I was shouting about, that it is an experiment which is showing that uh, departure from classical physics. Light is not showing wave property. Light is showing the material property, because it's an experiment of light is, if it is a wave in nature, then it is a scattering process. But with scattering theory, I cannot explain electron emission. I have to consider this as a collision process between photon and electron. Who collides? Matter collides. Okay, that is the main lesson from the photoelectric effect. So what it shows is, look at the picture here. This is a classical physics concept, waves and matters. Waves are different, matters are different. But what the moment I cross 1900, my concept is shattered. That at least one experiment is there where a wave is showing the property of matter. Now one more experiment is there in this round. That is the further in just 20. You see, Einstein has got a Nobel Prize for this photoelectric effect concept. Okay, for in 1905 he proposed it. He got it later on, but in 1923, to support this idea of Einstein, another experiment was done. What is the idea? What is the concept we have generated? That a wave can sometimes show the property of matter. Okay, this was further established through another experiment that was done by H. Compton, an American scientist, in 1923, and that is our next job, is to learn. Okay, you see, each experiment, as I promised you, each experiment will give you a lesson. So that lesson we have got from photoelectricity. It's a known experiment, but I hope you have got the message. Message is clear. It's an experiment showing the departure from classical physics. A wave can show the property of matter. A wave can collide, and a photon, a piece of energy of light is called photon. Photon is making collision with electron. Who collides? Matter collides. So it's an experiment, and no wave is showing the picture of matter. Okay. So it will be further established to Compton effect, but we'll discuss that in the next day. So I request you to solve this similar problem, okay, as I've shown here. I presented it for 486 nanometer. My request to you is that you do it for 600 nanometer, the yellow light, and also for 400 nanometer, okay, and do it in electron volts. And in the next class, you show me, you share it me in my link, in my email ID, okay, or in the class link. Okay, so thanks for the time being. So we'll come up next day with the Compton effect study. Thank you.